Hello everyone, this is Cody Jackson for Codemom, and we are continuing our look at practical information technology. This time we're going to be looking at digital electronics. Now, like last time we were talking about basic DC electronics theory, this isn't going to be completely accurate in terms of reading a book. This is going to be stuff that is basically put into layman's terms and may not necessarily be completely book accurate, but hopefully it gets the point across so that the average person who doesn't know anything about electronics and probably won't ever touch it again, at least understands what we're talking about. So, digital electronics is a subset of electronic theory that deals with digital signals. Digital signal is a discrete value at a point in time. So, if you are looking at a sine wave, hopefully everybody knows what a sine wave is. It goes up and it goes down, your peaks and your valleys. A discrete value at any point in time would basically be at any arbitrary time along that sine wave, you take a measurement of that sine wave and see what the voltage reading is, assuming it's voltage. That's going to give you a digital value for that sine wave at that point. Higher sampling rates means higher fidelity because you are better accurately tracing the sine wave signal. We're going to jump over to just a general search of the digitizing the sine wave, just so you understand what I'm talking about. So in blue, you have your analog sine wave. It goes up and it goes down, and it's infinite values at any point across there. Digitizing it means you're sampling in green at a particular point to figure out what the value is. And so you can see how the green line has the same shape as the sine wave, but it's not as defined as the sine wave. If you look at this other picture, you can see that there's a higher sampling rate, and so it better shows the sine wave pattern versus this kind of blocky step pattern that you see here. And so that's what digitizing basically means. So, in digital electronics, we're still using voltage, we're still using current flow to do our work, but we're only looking at a change in voltage rather than absolute values. Again, this is part of the deviation from book learning and layman's terms. So, assume we are expecting a digital value of 0 for off, 5 volts for on. Basically on or off. In an analog system, you would get line noise and induced voltages and stuff like that that may change the actual measured values. And if you've ever used a voltmeter, you may have seen this where it kind of bounces around and it's not a constant value. It may kind of fluctuate a little bit. So based off of that line noise and stuff like that, we may see a difference of, in this case, 0.3 volts. If that's the case, you may have a off value that's anywhere from negative 0.3 volts to positive 0.3 volts, but not necessarily 0 all the time. And your on voltage may vary between 4.7 volts all the way up to 5.3 volts. So obviously if you're expecting 5 volts, but you're only getting a 4.7, it's not going to say that it's on. It's still off. But if you only care about the difference of 5 volts, then it doesn't matter what the true value is, as long as you are looking at a difference of 5 volts either way. And that way, you could have a negative 0.3 volts to a positive 4.7 volts, and that's still an on or an off to an on signal. And so it kind of balances out because you don't care about the absolute values, you just care about the change between the values. Again, not completely accurate, but good enough for what we want to talk about. So why is digital better? Well, we talked about how analog signals are more prone to noise, and they're generally harder to work with because it's analog. It can have an infinite number of values at any given point, and with the noise on the line, you're not always able to verify what values you're going to be getting. Even if you're just looking at the peak values, line noise can affect the true measure of peak, which we just talked about. Could vary from 4.7 to 5.3, but the peak value you're looking at is 5. Because we are looking at discrete values at a point in time, digital signals are immune to noise. Either the signal reaches a particular value or it doesn't. And the variance of that signal can be measured more accurately than the true value. So if you're just looking for a change in value of 5 volts, you can measure that regardless of the line noise. Digital systems are easier to design. You only care if it's a high or a low. Hence, that's where binary comes in. If it's high, it's 1, it's on. If it's 0, it's low, it's off. And so digital basically means binary. And so you're only looking for that high or low value, however you have defined it to be. Noise immunity can be handled easier in a digital circuit. You can have filters, which will eliminate the noise prior to measurement. You can also have filters in analog systems, but because of that arbitrary high-low values that we've decided, your filters can help set up that high-low value. Your signal variance can be measured, as we've seen, so the induced noise on the line is ignored. Again, you don't care about the minor fluctuations caused to the signal because of the noise. You're only looking at, does it meet a certain threshold, and is there a substantial variance between the high and the low? In digital systems, information is easily stored. Binary data, it's binary. As long as you are able to show an on or an off value, you can use anything that can show that. So they have shown that you can make DNA computers, you can use magnetic bubbles, you can use light. If you wanted, you could use leaves on a tree to simulate it. And, if the front-facing shiny part of a leaf is on, then the duller backside of the leaf is off. And so you can use leaves to show binary data. Digital storage, depending on the medium, can be less prone to long-term damage and degradation. Now, if you consider a magnetic tape, magnetic tapes came about when analog basically ruled the earth. And it's the fluctuation of the magnetic waves within the tape that stored the data. You can store digital data on there too. It's just looking, is there a pulse or not? And so in that case, tape degradation occurs regardless of the type of data that's on there. But if you look to CDs, CDs are purely digital, and they have lifespans in the decades. And they're a little bit more resistant to damage than magnetic tapes are. But, as I said, you can store digital data on anything. So you can have a flash drive that'll last 100 years, as long as it's not exposed to, elements and X-rays and things like that that could fundamentally damage the data. If you ignore that type of stuff, the physical SD card is going to last effectively forever. Digital signals are more accurate. Now, you can debate that because analog signals are infinite and they're able to hold data, but there's a limit to the inherent precision that you can get from an analog circuit, which is usually about 3 decimal places. And so if you've ever seen reports of data, 3 decimal places is about as high as you're going to get. But digital signals are going to allow you to have a much higher precision because of noise and the circuitry used and things like that. And so that's why you get these decimal places that are like 12 points out, because it's simply much more accurate at that point. And probably the biggest reason digital is better, you can program digital. It's very easy to program something with software that doesn't necessarily have to deal with analog signals. Analog is difficult to work with. Granted, the real world uses analog. I mean, that's how it is. But for what we can control, digital is better. So I put an example of here of a pulse width modulator. So if you think back to these sine wave example that we had, where you have those distinct little hops between voltage ranges for a digital signal, that's basically a pulse width modulator. Well, it's a sine wave in reverse. So here's a picture. You got your digital signals in blue, and you've got the what's the equivalent of the analog signal coming out. So I don't want to get into details, but just recognize that based off of the width of a digital pulse, that's what your output signal is going to be. So a blue, we have a pulse width of, what's this, maybe half a second. And so that's going to take our output voltage from 0 to 0.5 for maybe about a second. And then we're going to do another pulse for another half second, and that's going to raise it up to nearly 1. And then it's going to stay constant, and then we're going to pulse it again, and we're going to get up to 1 volt, and then we start putting in negative voltages, and that's going to drop the output voltage. So using pulse width modulation, we can simulate a analog signal on the output simply based on how long those pulses last. Hope this didn't scare you off. Just kind of showing that what you can do in analog, you can do in digital, as long as you understand what's going on. So there are some limitations to digital systems. The switching elements for digital systems can be expensive, and that ranges from data storage to fast processing to just about anything. Now, there are certain aspects to digital theory that means as time goes on, systems become more complex, but they also become cheaper. They're saying right now that the phone that's in your pocket is something like 4 times more powerful than the computer that Apollo missions took to get to the moon. That may be, but your smartphone isn't going to take a spacecraft to the moon because it doesn't have the same the same engineering design in terms of fail-safes and stuff like that. That's neither here nor there. As I said, the real world is analog, so your input and output systems of digital systems require some conversion. And no matter how accurate your digital signal is, no matter how fast your sampling rate is, you're never going to get the true infinite values that a analog signal will give you. So, we're going to talk about some of the components that are used in digital systems, just so you have an understanding of what's going on in your computer. Diodes. So it's a semiconductor, and we talked about how a semiconductor, depending on how it's used, can be an insulator or it can be a conductor, either stopping or allowing flow of electrons through it. So a diode is a semiconductor of two different types of silicon, P and N. Don't worry about what those mean. It's just signifying that we have two different types of silicon that only allows current flow in one way. Not totally true. You can get reverse flow, but we're talking at much higher voltages than normal operating. So for a traditional diode, approximately 0.7 volts, positive to negative, across the diode allows current to start flowing through it. If you reverse the voltage, then due to magic inside the diode, you get a backup of electrons, and so the flow of electricity through the diode doesn't occur. And so you do not get a reverse current through the diode. Like I said, if you increase the voltage high enough, you can overcome that backup and the current will start to flow to a certain point, and then it's based off of the temperature as to how much current flows through it. If you want to get into electronics, you can start learning about different types of diodes, like Zener diodes, that have a specific reverse voltage that allows them to work either as a regular diode or as a reverse diode, depending on the situation. Lots of other stuff. We'll jump over to Wikipedia just for a little bit more clarification of diodes. If you're looking at a circuit drawing, a diode is going to look like this, an arrow with a line across it. The line basically shows that current flows from one end to the other, and then that line indicates that it's not going to be coming back in that other direction. If you want to learn more about diodes, take a look at the Wikipedia page. It's going to give you some animations of how the diodes work in terms of voltage and current, as well as some pictures of different diodes and even vacuum tubes, which were the precursor to diodes, or I should say semiconductor diodes. All right, so there was a technical error in my recording, and I recorded the pieces that I didn't want to record and did not save the stuff that I wanted to record. So hopefully there's not a bad transition, and we'll cover all of the information that we need to. We're going to finish up by talking about logic gates. Logic gates use diodes and transistors in different ways to perform logic operations. Those logic operations are AND, OR, and NOT. There's also NAND, which is a not and NOR, which is a not or. And when we're talking about the functionality, it's like addition, subtraction, multiplication, stuff like that. If you have done any programming, then it's the same concept. An AND is if all of the inputs are true, then the output is true. If any one of the inputs is false, then the output is false as well. Or any of the inputs can be true, and you have a true output. If none of the inputs are true, then it's false. And then a NOT is just a reversal of the input. Just to help, we're going to jump over here to the Electronics Coach website so you can see some diagrams of what we're talking about. Logic gates, there's a picture of what it looks like. Here is how it would look like if you had your diodes to create it. You have three diodes in parallel. You have your output coming in and your resistor to ground. Any one of those diodes input can be true. You have an input there, and you'll get an input out. There's a truth table. Truth tables basically tell you what is the logic within the gate to provide a given output. You can also make transistor or OR gates out of transistors. Same concept. They're all in parallel. Whatever the output is what you're going to see on the output. Guess that makes sense. Whatever you have coming in, if there's a single transistor that is passing current, then you will get an output. Here's how they would be arranged in a typical integrated circuit. You have 4 OR gates in here, and you can use any one of them for your purposes. Obviously, as you get higher forms of integration, you can pack more and more of these gates within a particular chip. AND gate, same thing. Here's it using diodes. You can also use transistors for it, as shown here. All that stuff. Here it is as an integrated circuit. A NOT gate is just an inverter. Whatever goes in is the opposite coming out. And using a transistor as an inverter is shown here. So that's about it for this video. We talked about the basics of digital versus analog, why digital circuits are generally better than analog, and some of the digital components that you'll find, diodes, transistors. Just remember that regardless of all of the gates and transistors that are being used in digital, we're looking at either maximum current or no current. We don't care about any varying value in between. That's all more analog components. We just care about on or off. Next time, it's a crapshoot. I don't know what I want to talk about. If you have any preferences, anything that you want to know about, let me know. Otherwise, I'm going to take a look through my books and other references and see what might be useful as a practical information technology video that can apply to, general audiences within the IT realm. Until then, have fun, keep learning. Thanks. Bye.